We are going to start with where we left in the last class. We were discussing diffusion with homogeneous chemical reaction. Now, as we have discussed in the last class, heterogeneous reaction takes place only at a specific location, most commonly on a catalyst surface, whereas homogeneous chemical reaction takes place throughout the medium, and we are going to deal with such a reaction where the reaction takes place everywhere in today's class. So, for that we have a liquid, let us call it B, in contact with a gas. The gas dissolves in liquid B and then starts diffusing towards the bottom, which is situated at Z equal to L. As it diffuses through the liquid, it undergoes a chemical reaction A plus B giving AB, and the reaction rate per unit volume is given as K1 triple prime Ca. I would again bring to your notice the triple prime, which is generally for homogeneous reactions. So, it is reaction rate, that means moles per unit volume per unit time. So, that is the reaction rate. Now, in order to analyze such a system with shell mass balance, what we can do is take a strip of thickness delta Z and find out all the in and out terms along with any source or sink. Unlike the two problems which we have analyzed in previously, in this case we will have to see that whether or not any reaction, that means a source or sink term, present in this control volume. One more thing is, as we have mentioned, that the first aim is to find a relation between NA and NB, or to decide whether or not to include the bulk term, the mass transfer term due to bulk flow. Now, there are several situations which would enable us to neglect this term. It could be a diffusion only process. If it is a diffusion only process, if it is mentioned that it is a diffusion only process, then obviously this term will not be present in the equation for NA. On the other hand, several other possibilities exist. For example, this XA could be very small, that means it is a very dilute solution, and if it is a very dilute solution, then you can imagine why the diffusive flow of A through B is not going to impose any bulk flow. The first problem that we have analyzed, that is a gas, a liquid rapidly evaporating, and the vapor that is formed is diffusing through the tube. So, in that case, the rapid motion of A molecules will induce a motion in the B molecules as well. So, if that is not the case, if it is a very slow diffusion case, in that case this term, the significance of this term would be small compared to this term. So, small values of XA, that means it is a dilute solution, or if it is a case of diffusion only process, in those cases these term can be neglected. There exists a special case in which case NA is equal to N minus NB. This is a special case which we will discuss next. So, in this specific problem, we are going to assume that A is sparingly soluble in B. So, if A is sparingly soluble in B, then this whole term can be approximated to be equal to 0. That means the effect of any bulk flow is probably non-existent, and in that case the governing equation for NAZ would simply be the diffusive term, nothing else. Next, we deal with straight away the balance terms. So, NAZ, which is moles per unit time per unit area. So, in order to find out the total amount which crosses this Z equal this boundary, it should be multiplied by the cross sectional area minus NAZ, with the one that is coming out evaluated at Z plus delta Z. Should there be any other term accumulation depletion term? In this equation, should there be an accumulation or a depletion term? A depletion term, only because it is a homogeneous reaction. So, the reaction takes place throughout the medium. So, as a result of that, we can substitute the reaction this one minus K 1 triple prime C A S delta Z. So, collectively this is the volume. So, this makes it moles per unit time. At steady state, the sum of all these would be equal to 0. Now, the next step is obvious. We are going to divide both sides by delta Z, take in the limit when delta Z tends to 0. So, what I am going to have on my left hand side is minus d dz of NaZ, and we already know what is the expression for Na going to be in this case. So, if I substitute everything and simplify, the next step would be ultimate governing equation. Assumptions involved, it is a diffusion only process, and we make it diffusion only by stating that A is sparingly soluble in B. So, the movement of A molecules through B, through the liquid B, will not create any bulk flow of B. Now, do you have any question up to this point? Derivation of this equation. If that is the case, then we are going to need certain boundary conditions, two boundary conditions. The first boundary condition, it has been stated that the concentration at Z equal to 0 is maintained at a value equal to Ca0. So, this is already there in the statement of the problem, that Ca is equal to Ca0 at Z equal to 0. Can you tell me what would be the second boundary condition? I will put the figure back again for you to find out. From this, would you be able to say anything about the second boundary condition? Okay, at someone suggested at Z equal to L, Ca is equal to 0. Any opinion about that? He said that at Z equal to 0, Ca would be 0. Is that true? Okay. Can you this is not right or correct, but can you tell me how to make Ca equal to 0? What do you have to say to make Ca equal to 0? The reaction has a finite rate. So, it is unlikely that all A molecules will be converted to B by the time it reaches Z equal to L. Okay. So, what do we have to say so as to make that Ca equal to 0 at Z equal to L? Z is very large. So, it is a very deep pool of B. Only if that statement is made, you can say Ca equal to 0 at Z equal to L. But that is not the case. It's a finite depth. It has a finite depth. So, what can you say about the other boundary condition? Anything else that comes to your mind? Just think about it. A molecules diffusing through B, as it diffuses, it undergoes reaction. The reaction rate is finite, it is not infinite. So, some A molecules, a large number of A molecules will come in this direction, and as it moves, the number of A molecules will decrease, but when it reaches here, there will still be some A molecules which are unreacted. So, there would be a steady state concentration of A at Z equal to L, which is unknown to us, which would depend on the value of L, the value of diffusion coefficient, and what else? Which one? The value, the magnitude of K. So, the steady state concentration of A at Z equal to L will depend on the depth, the reaction rate, and whatever be the value of Ca0 at this point and the diffusion coefficient. So, what is going to happen to the molecule which has reached to this point? Can you say anything about the motion of that molecule when it reaches Z equal to L? Anything like the process, a stream of A molecules coming, and as it is coming down, some of them are depleted, converted to AB. When it reaches to z equal to L, would you be able to say anything about their motion after that? All right. Is it equivalent to this situation in heat transfer? In this wall, the temperature at this point is less than the temperature outside, and over here there is some heat generation or depletion. Let us say heat depletion, if it is possible by some means. So, that the energy would flow in this direction, and as it flows, the amount of energy will reduce and it will come to this point. If I make this insulated, what is the boundary condition that you are going to use here? Minus dt dx at x equal to whatever that location is equal to 0. What is the physical statement of this condition? No? If it is an insulated surface, what can you say about the heat flow through this wall? It is 0. So, it is no heat flow through this surface. It is going to act as an adiabatic surface. It is perfectly insulated. All right. If we understand that, then what is, let us say we are doing this experiment in a glass beaker. So, what is this surface to the A molecules? The diffusing A molecules through the liquid is going to encounter a glass wall which it cannot penetrate. So, if it cannot penetrate that, then this at this wall something similar to adiabatic wall in heat transfer must exist. That means, there is no flow of A molecules through this, that is not possible. So, the missing boundary condition, now you can tell me what is going to be the missing boundary condition. dCA at dz at z equal to L would be equal to 0. So, it is exactly similar to the one that you have done in heat transfer. If it is some surface at which it's in the A molecules cannot penetrate, then the flux at that location would be equal to 0, the mass flux at that location would be 0, and we already know that the mass flux can be given by this one. So, these are the two boundary conditions which one can use for this specific problem.
So, it's not hit and come back.
Okay. The question is, I suppose when you start with 3 molecules, it becomes 2 molecules, it becomes single molecule at any instant of time. The question is it going to come back? Okay. So, can you answer me whether it is going to come back or not? What makes you not come back to the solution again? Okay. So, the concentration is very high on this side, it is progressively decreasing as we move in this direction. And we have already said that diffusion is inherently a slow process. So, this molecule is not going to have enough kinetic energy so that it can bounce back, and it can definitely not move in this direction, as in that case it would move against the concentration gradient. In the concentration gradient will not favor its motion from this side to the others. So, I rephrase his question. So, am I not going to get an accumulation of A molecules on this surface with time? What he said is that this molecule is, can it bounce back? We have found out by our discussion that it cannot bounce back, but the number of molecules will obviously start to accumulate at this point. Okay. So, what someone is saying that at steady state, the definition of steady state tells us that the concentration at any location will remain independent of time. I mean, they may differ depending on the location, but at any specific location its concentration would not change. Fine, that is a definition of a steady state, but that still does not answer our question, what is going to happen to the molecules which are coming to this point.
Some of them will remain on reaction.
Okay. So, we have two opinions, some of them will remain on the surface, some of them will bounce back. Anything else? Okay. So, what is going to happen is that at even the A molecules which are reaching this surface, they are also going to react. Okay, it's a homogeneous reaction, it takes place everywhere. So obviously the A molecules will also react, and when it reaches steady state, one can also say that the amount which is coming to the surface is going to be equal to the reaction rate, to the rate at which it is reacting. Otherwise you won't be able to maintain a steady state. Okay. So with these two conditions, one would be able to solve the concentration profile, which I am not going to write. Only thing is, we are probably interested in what is the molar flux of A at Z equal to 0. That means at this location. If you are to find out what is the molar flux of A at Z equal to 0, that means you are trying to find out what is the dissolution rate of A at Z equal to 0. So how do you evaluate the dissolution rate? The dissolution rate of A in B at Z equal to 0. You already have obtained with the boundary conditions the concentration profile. Yes, what is dCA dZ evaluated at Z equal to 0 multiplied by minus DAB. So minus DAB dCA dZ at Z equal to 0 would give you the amount of A which is entering the solution per unit time. It's exactly similar to if you would like to find out what is the heat that's coming in or going out through a surface, through an interface. Its temperature gradient multiplied by minus K at that location. So here also, if you would like to find out the dissolution rate, it would simply be minus DAB dCA dZ at Z equal to 0. So that's about the main point to remember in this case is, if it's a homogeneous reaction, there would be a source of sink term. If it's a heterogeneous reaction, as you have seen in the last class, it's going to come through a boundary condition. All right. So that's the difference between homogeneous and heterogeneous reactions applicable to mass transfer. This will be later. Now let's think about a very common problem in chemical engineering. It's diffusion and chemical reaction inside a porous catalyst. We all know how catalysts are important in chemical reaction, in chemical industry, and in so many other places. Everyone is trying to make the best catalyst possible. So how do you quantify whether or not your catalyst is performing properly? Now if you are making a catalyst, suppose you have to make the catalyst with material A. You can prepare material A in many different ways. So if I say that this is material A, 1 kg of material A I am giving to you, you make the best catalyst out of it. That means you are only going to do some structural changes to the catalyst. And in most of the cases, not all part of the catalyst are active. Not all points on the catalyst are active. It's only going to have certain active sites. Okay. The catalysts are generally porous in structure. So you have a catalyst porous in structure, active sites may be within the pores, some of them may be outside as well. So the active sites are well distributed inside the pores as well as on the outside. So if you are to make a very good catalyst out of it, what are the changes, what are the steps that you would like to follow? Using your common sense, give me the answer.
Maximum surface area.
Maximum surface area. So how do you make maximum surface area? That means probably the better answer would be maximum surface area per unit volume of the catalyst. So you would like to make it maximum surface area per unit volume. How do you make that? Make it a powder, as small a particle as possible. Now even after you make a powder, there would still be certain pores inside it. So not all the active sites will be exposed to the reacting mixture. Okay. Suppose it's a reaction between A and A going to B, and that reaction can only take place when you are at the active site of the catalyst, and you have done whatever you could by making it's a granular, very fine powder, but you still have certain ports, certain ports where diffusion has to take place before the reaction can occur. If you have to define an effectiveness, what would be the definition of that effectiveness of the catalyst? So you understand the basic principles. You think about it. You are defining an active surface area. So what could be the, whenever you are defining an effectiveness, the denominator has to be maximum. So such that its effectiveness can maximum be equal to 1. So how do you think that you can make the denominator the maximum? What is reducing the reaction rate if you have a porous catalyst? The diffusion through the pores. A molecules will have to diffuse through the pores to reach the active site, on which it is going to get transformed into B, and then B is going to come back out of the pores into the product stream. So how do you make it? What would be the ideal condition? Ideal condition for a catalyst? All the active sites are exposed to the reactants. The reactants will not have to go through any pores or any diffusive process. So if you could make such a catalyst where all the active sites are exposed to the reactants and products, that would be the maximum possible conversion you are going to get. So that should be in your denominator, and the numerator, whatever be the rate that you are getting with the present set of conditions, with the present structure of the catalyst that you have. So I am going to define an effectiveness in this way, that it's whatever be the reaction rate that is taking place with the present condition, and the denominator would be relative to if all the active sites are exposed. That means if all the active sites are such that no diffusion is necessary. That is the situation at which I am going to get maximum conversion. So that part is straightforward. So that means in order to evaluate the numerator, I would have to find out what is the concentration distribution of the reactant or the product inside such a pore, because unless and until I find out the concentration profile inside the pore, I would not be able to evaluate what is the concentration of the reactant at the active site, because the reaction rate ultimately is going to be proportional to, if it's a first order reaction, what is the concentration of the reactant at the active site. So in order to evaluate that, I would have to have the complete profile with me inside such a pore, such that I can evaluate what is CAS, that means Ca, concentration of A on the surface. Then I use the proper rate equation which is given to us to find out what is the conversion. Multiply that with the proper volume. It is not going to be only volume, you also have to think about what is the surface area, active surface area per unit volume, because is it a homogeneous reaction or a heterogeneous reaction? Heterogeneous reaction, because it only takes place at certain points, not everywhere. So if it is a heterogeneous reaction, then you are going to have a reaction rate constant which will be generally denoted as, let us say, K1 double prime. So K1 double prime multiplied by Ca would give the rate. Now this is going to be amount converted per unit area, but not all the area is active. So this factor has to be multiplied by something which is specific to the catalyst, that is surface area of the catalyst per unit volume, which will change depending on how you process the catalyst. So whatever be the reaction rate which is based on per unit area has to be multiplied by area per unit volume of the catalyst to make it number of moles converted per unit volume of the catalyst. So someone has to evaluate what is the ratio of active surface area relative to the total volume of the catalyst by some other means, and that information has to be supplied to the engineer to find out what would be the rate, what would be the amount, what is the rate of conversion of A into B. So we are first going to derive what is the concentration profile with the help of some sort of a factor called A, which is surface area per unit volume of the catalyst. Now when I say per unit volume, I include both the solid and the pore area together. Okay. So if I say the active surface area per unit volume is this much, then this per unit volume includes both the pore area as well as pore volume as well as the total solid volume. So, we'll start with let us say the reaction is such that I have a spherical, roughly spherical particle and concentration at some with some concentration, and the reaction is A going to B. The reaction takes place only inside the pores. So, if I magnify this region, the pores are in most of the cases irregular. Okay. So, the reactant has to move into the pore, reach the active site, get converted, and the product will come out. So, this is a magnified view of a very small point on the catalyst surface. Let us, for the argument's sake, we take this to be perfectly spherical. So, if it is perfectly spherical, and what kind of a shell balance I am going to use? It is just a spherical shell of thickness delta r. So, the amount that comes in is going to be NAR multiplied by 4 pi r square evaluated at r. The one that goes out is going to be NAR times 4 pi r plus delta r whole square, everything evaluated at r plus delta r. Then with this I am going to find out the profile. Here I am taking the assumption that it is a diffusion only process. Can you tell me whether this is justified or not? Is it a diffusion only process? What makes it diffusion only process? I have flow of A or maybe A and B together towards the spherical particle. The reaction takes place within the pores, within these small pores, and I am saying that it is a diffusion only process. Is it justified? Since the pores are very small, in most of the cases the pores are closed. So, the bulk flow inside the pore is probably non-existent. So, we can safely take it to be as a diffusion only process. Now, it is a reaction inside the pores, the reaction is taking place. Now, we do not know where exactly it is taking place. Is it taking place here, here, or any point in between? And again, the size of the pore is very small compared to the size of the particle. So, it would be safe to take this as a homogeneous sink term. Now, when can I take this as a homogeneous sink term? When the pores are very small. All the property, diffusivity, etc., that we are going to mention for this is some sort of an average property for the catalyst. You can say that this is not holding the continuum, because if I take a shell like this, then part of the shell is going to consist of solid, part of it is going to be pore, and then again solid and pore. So, how do I maintain a continuum? So, this is only an approximate first order analysis of a catalyst, where everything is taken as a continuum. All the properties that we are referring to is some sort of an pore averaged property. So, the diffusion coefficient, etc., is going to be some sort of an average property. We have a similar situation that we dealt with in heat transfer. If you remember, like there we were analyzing the flow and reaction, flow of a hot mixture, hot fluid mixture through a number of particles. Now, when we the figure was something probably like this, if I remember it correctly. Some reaction was taking place in one zone, no reaction was taking place in the zone after this and the zone previous to these. So, these are dummy particles on which no reaction takes place. These are the catalyst on which reaction takes place, resulting in release of some amount of energy, and these are dummy particles again. So, when we are taking a strip and making the heat in minus heat out plus generation is equal to 0 at steady state, and we are using we are writing heat in as K effective times dt d whatever dz at z equal to, let us say, 0 or z equal to some z. What is this K effective? Because this K effective consists of a particle some gap and a particle again. So, this K effective essentially gives you whatever would be the thermal conductivity of the average medium. So, if I average across the cross section, this is the value of K that I am going to get, and this will have two components, one is K for the particle and one is K for the vacant space, or K for whatever, it is not vacuum, K for where you do not have any particle. If you average them out, this is what is going to be K effective. Similar to that approach I am going to use here as well. So, the diffusion coefficient that I am going to take, it is an effective diffusion coefficient, and we understand that continuum is not possible, but it is going to be, so that is why it is going to be only going to be an approximate analysis of the concentration profile inside such a pore. So, with those assumptions, the governing equation would be this is the reaction rate. Now, we understand that this, whenever we are going to replace this with dCA dr with minus dCA dr, since it is a diffusion only process, this is an average diffusivity. So, simplification of this equation would simply give you dA, that means diffusivity of A inside the pores 1 by r square now we have to define R A as if it is a homogeneous reaction. We understand that on a molecular scale it is heterogeneous, but somehow I have to, in order to make this equation right, this R A has to correspond to that of a homogeneous reaction. So, I know that R A has to contain K double prime. So, this is per unit area basis. Now, that per unit area, the reaction rate per unit area has to be converted to per unit volume, and when I would like to convert it to per unit volume, the concept of active area of the catalyst per unit volume would come into picture. That means, if this K has to be multiplied by, let us say, a factor A, where A is defined as active area of the catalyst per unit volume of the catalyst, this volume including both the pores and the solid, then the reaction rate, instead of being a heterogeneous reaction, I convert it to homogeneous, because now it is going to become moles per unit volume. So, it is K1 double prime Ca multiplied by A. When I say K1 double prime Ca, it is moles per unit time per unit area. I multiply that with A, which is area per unit volume. So, by introducing a factor A into this expression, I make it moles per unit time per unit volume, okay, and only then this reaction is right. Is that part clear? Okay. So, this is an artificial quantity which I am introducing here. This A someone has to find out from structure analysis of the catalyst. How many active sites you have? How many active sites you have per unit volume of the catalyst? If I know that, and then I multiply my heterogeneous reaction rate with that factor, then this becomes homogeneous reaction. It is again an approximate analysis, not valid at every point, but it is some sort of an average over the whole thing. Is it clear? So, the reason why the A has to be introduced and the importance of the factor A, and this would be a very effective way of characterizing your the catalyst. The larger the value of A, obviously the better would be the performance of the catalyst. So, this equation with this form, R A substituted with minus of this, can be integrated, and the integration, that part I am not going to talk about. Only thing is, what are the boundary conditions that one can take? One is that Ca is some known value at small r equals capital R. So, this is the surface concentration of A on the catalyst pellet, on the spherical catalyst particle, which can be measured. This is the size of the catalyst particle. I would need another boundary condition. Would you be able to suggest what is that boundary condition? You can look at the nature of this equation and find out what kind of boundary condition would help you, or you can think physically as well. What would be the missing boundary condition here? Anything? Let's say we at r equal to 0, dCA by dr equals 0. So, essentially you are saying that at r equal to 0, Ca is finite. Is that a valid boundary condition?
Because in equation if r is equal to 0, then denominator is 0.
Okay. What was a similar situation in heat transfer? Think of the case of the first problem. I think what we have analyzed for heat generation in a thin wire. Okay. At the surface of the wire, the temperature could be specified, or it could have a convective condition, whereas at r equal to 0, the temperature cannot be infinite, the temperature has to be finite. Exactly similar way, this is a spherical system. At the surface, either your concentration would be specified, or you can use a convective mass transfer condition at this surface, but at r equal to 0, C has to be finite. So, that those are the two conditions which can be used.
Finite does not mean constant. dCA by dr means Ca is constant.
I agree. Agreed. Ca is finite. Fine. 100% right. Ca has to be finite. So, if Ca is finite, then you would see that one of the constants, one of the constant of integration, you can equate it to be 0. That means, if you remember, like there would probably I am not saying some sort of a this form is going to come in your expression for Ca. So, at r equal to 0, since Ca has to be finite, agreed, it has to be finite, then you can equate C1 to be equal to 0 as you have done before. So, in a similar in this way, you would be able to find out what is the concentration distribution, and it is going to be a sine hyperbolic form, but that you can see in your textbook. I would like to find out what is the molar flux of A at this surface. With your Ca function of several other things known to you, would you be able to find out what is WAS, that is molar rate of A at r equal to 0? Would you be able to evaluate this? Again, the significance of this WAS is whatever be the molar rate at the outside of the catalyst particle, because at steady state, that is the amount which is converted to B. Is that statement correct? I will repeat it one more time. If WAS is the rate at which A particles are coming to the outside surface of the catalyst, this, if I can evaluate that, this would be the total amount of A being converted by reaction. Is it all right? Because in order to maintain steady state, whatever be the amount of A particles that are coming to the catalyst, outside of the catalyst, all of them must convert to B in order to maintain constancy in A concentration throughout this catalyst particle. So, I would only like to evaluate what the amount of A which are coming to the surface. And how do you evaluate? Knowing Ca as a function of several other things, how do you find out WAS? One more time.
dCA by dr
dCA by dr R equal to capital R into dA and is it going to be small a? Should I bring small a or something else? Pi r square or something else? 4 pi r square. Okay. Let's see if this is right or not. So 4 pi r square would give me meter square. What's the unit of DAB? What is the unit of DAB? What's the unit of kinematic viscosity, which is mu by rho, meter square per second. Kinematic viscosity and diffusivity, they are fundamentally of the same nature. So, it is meter square per second, and dCA kg moles or let us moles per meter cube, and I have another meter here due to this R. So, what you have here is moles per unit time. So, that is the number of moles of A which is reaching this per unit time. So, this is what we would like to find out. Now, is A somehow included in this? That A, the factor A, because this factor A gives us what is the pore, the shape of the pore, the effect of the pore on the whole process, but I do not see any A here. Okay. So, CA obviously will be a function of A. So, that is already there according to our governing equation. So, this is what you are getting really. So, if I am defining an effectiveness of the catalyst, this WAS would be my numerator. Now, how do you express denominator? What would be the denominator in this case? The denominator simply, as we have discussed before, it is going to be if all the pores, everything is exposed, then you are going, whatever reaction that you are going to get, whatever the conversion that you are going to get would be the denominator. So, what is the, you know that your reaction rate is K1 double prime Ca, all right. So, this is if all the pores are exposed, what kind of area are you going to get? What is the area that you are going to get? What is the active surface area of your catalyst? No, the A is defined as the A into volume. So, A into 4/3 pi r cube, right, because this is your surface area per unit volume. So, this A times 4r cube would give you the active surface area. Now, I multiply that with K1 double prime Ca. What should be the subscript of Ca? What C am I going to use here? Pardon me? No, Ca, you are saying that it should be CAS. Why CAS? Because we assume that all the active sites are exposed now. So, if all the active sites are exposed, they are going to be exposed to whatever be the stream of A that is coming, and we have said that Ca is equal to Cas at small r equals capital R. So, at this location, if your concentration of A is taken to be equal to Cas, then this should be equal to Cas. So, this would define the effectiveness. This eta is known as the effectiveness of the catalyst particle that you have. So, effectiveness simply gives you whatever be the rate that is actually taking place divided by whatever be the rate if you do not have any diffusional resistance to the process. diffusion is nothing but adding an extra layer of resistance to the whole process. So, if you could somehow remove that diffusional resistance, that is going to give you the maximum conversion. So, that is why it is going to be in the denominator, and this expression for eta would be of this form, and the final form is again available in your text. Finally, a very quick discussion about a problem. I will give you the answer for you to practice on. It deals with our lungs. Okay. On one side of the lung tissue, I have air which you breathe in. On the other side, the tissues are connected to the bloodstream. What they would do is, the oxygen from the air would pass through the tissue, would be taken up by the blood, and it will go to the places where they are required. So, let us say the concentration of air on this side of the lungs is Ca0, which is known to me. On this side, in order to maintain proper conditions, the blood concentration at this interface should be equal to Cal. What I am interested in is, what is the oxygen for these two conditions, what is the oxygen assimilation rate by the blood per unit area of the lung tissue. So, its assimilation rate per unit area of the lung tissue. Is the problem statement complete or something is missing? I specify it is a Ca0 on this side, Cal, which obviously would be lower than Ca0, and oxygen from air passes through the tissue to the blood with concentration Cal. I would like to find out how much oxygen is taken up by the blood per unit lung tissue, per unit area of the lung tissue. Are any information missing here, or do you think the problem is more complex than it appears? So, what are the things that is missing, that are missing? What is K? Suppose I give you DAB, where A stands for oxygen and B is for the tissue. So, the diffusion coefficient of oxygen through the tissue, lung tissue, suppose that is also known to you. Do you want any more information to solve the problem? Okay, L of the tissue, that is length or whatever thickness of the tissue, that is needed. Fine, that is also given to you. So I give you DAB, L, Ca0, Cal. You would like to find out the diffusion of blood from the tissue blood interface to the blood. That information you want. Do you need that? So, you are saying that oxygen is going to be going to diffuse from this cell wall to the blood, and you would like to have an idea of the diffusion of that diffusion coefficient. First of all, would that be diffusion coefficient? What would you want? It's blood which is flowing. So, what you have in here is some sort of Newton's law of cooling, some sort of equivalent to Newton's law of cooling. So, instead of H, you would probably want Hm, which is the convective mass transfer coefficient, concentration of Cal minus whatever be the concentration at a point far from the blood. But I am saying that is probably not needed, because you ultimately have to find out what is the profile, what is the slope of the profile, concentration profile at this point. But there is still something which all the students of biotechnology should be able to tell me, something which is missing. Are these living or dead? I hope they are all living tissue. Okay, so a sync term, and why would that sync term be required? And what would tissue require or need? Okay. So, as the oxygen molecules start to diffuse through the tissue, some of the oxygen is going to be taken up by the tissue. Okay. So, there has to be something of a depletion of oxygen as it passes through the tissue. So, that rate you would like to have before you can find out what is the concentration profile. So, let us say the oxygen consumption in the tissue is K0 triple prime and the unit would be moles per unit volume per unit time. So, this is your oxygen consumption. How are you going to analyze now? How would you proceed if this is known to you? A cross section, the one that is coming in, the one that is going out, minus consumed. So, minus K0 triple prime multiplied by V. So, the one that coming in is Na, if I call this direction as Z, NaZ at Z multiplied by a surface area minus NaZ at Z plus delta Z multiplied by another surface area minus K0 triple prime. What should I write here? Delta Z into S is equal to 0. So, this is exactly like a homogeneous reaction which is taking place. More correctly, it is adding a sink term to the whole thing. So, once you want, and what should I write for NaZ? The whole form, diffusion form, or the bulk only? The NaZ equation contains two terms, the bulk flow and the diffusive flow. So, it is going to be diffusion form only. So, NaZ can simply be written by minus dAB dCA dZ, where A is the oxygen constant, A refers to oxygen. So, you substitute NaZ, proper form of NaZ, integrate the equation with boundary conditions. So, you get C of O2 as a function of Z. This is known to you after this exercise. Can you now find out what is the assimilation rate? You find out, you have already found out C of oxygen as a function of Z and other parameters, for example, K, dAB, L, etc. What is going to be the assimilation rate per unit area?
NaZ at Z equals to
Z equals to?
L.
So, assimilation rate would be nothing but NaZ evaluated at Z equal to L. So, that is going to be your assimilation rate. Is it clear? Whatever be the amount that is coming at this point has to be assimilated, taken away by the blood. So, if you can calculate NaZ at Z equal to L, that is going to be your assimilation rate, and I will give you the answer for you to check. It is going to be K0 L by 2 plus dAB by L Ca0 minus Cal. Okay. So, this would be the expression for the assimilation rate, and this would be in moles per unit area of the lung tissue, per unit area per unit time for the lung tissue. Any question up to this point? Thank you. We will continue with our studies of mass transfer. What we are going to look today is a situation which is very common in chemical engineering. In some chemical engineering problems, it is taken as an assumption, and in many of the cases it is a very valid assumption. The name of that situation is equimolar counter diffusion. As the name suggests, this arises when each mole of A, let us say, going in from the right to left, one mole of B will move in the opposite direction. So, in some situations, if you can maintain that condition, that for each mole of A going to one direction, another mole of B will be moving in the other direction, that situation is known as equimolar counter diffusion. Now, why spend any time on equimolar counter diffusion apart from it is going to give us some mathematical advantage flexibility while using the expression for, let us say, NAZ, that is the species movement rate from in the Z direction. Many of you have heard of distillation process, right? Distillation is nothing but if you have a mixture of two liquids and you would like to separate one from the other. Any idea how this is done? What is distillation? Okay. The simplest possible distillation apparatus that you can think of is, it's called a still. Okay. You have a container, that container contains the mixture of A and B, and you would like to separate A from B. Now, the first use of distillation column is for making alcohols. Okay. For a very long time, people know how to make alcohols from let us say a mixture which can be fermented, but it contains, among other things, two principal constituents. One is alcohol and the second is water. So, you would like to concentrate the alcohol. So, you put the mixture in a still and heat it. Now, what happens when you heat a mixture where there is a change, a difference in relative volatility? Now, what is relative volatility? We all know that each component has a specific vapor pressure. More the vapor pressure, is it easier to vaporize it or it is difficult to vaporize it? That is the basic principle of distillation operation. And what is the commonest use of distillation in today in chemical industry? Where you can find distillation? In petroleum, right? So, you start with the crude, and depending on, suppose it is a very large distillation column with 50 trays. So, you can take products from different trays, and depending on where you are drawing your product, you are going to get different streams. Okay. The top would be, I mean, you can have from aircraft fuel up to, what is the bottom product of a petroleum distillation column? It could be tar. Okay. So, depending on what is your feed stream, what it contains more, depending on that you are going to get different products at different locations. But how does it is connected with transport phenomena? Now, whatever happens on a tray in a distillation column is nothing but transport process between liquid and vapor. Now, what is the driving force for one component to move from the liquid to the vapor phase? The driving force for component A, let us say benzene, to go from liquid to the vapor phase. Why would a bottle of perfume, when I open it, my question is, if I open a bottle of a high volatile component, okay, why would you be able to smell it sitting over there? Diffusion. So, there is a concentration difference between the liquid phase and the vapor phase. So, if you have a concentration difference, that concentration difference in turn, the basic root cause is a change in chemical potential. Because of the change in chemical potential, a species moves from one point to another. But if you look at it at overall point of view, it is the concentration difference which drives the more volatile component from the liquid to the vapor.